Good morning, everyone. This is Ajanette, and I am here to do your chapter 13-14 lecture. We are going to be covering chapter 14, correlation, today. I need to confess I actually did this whole lecture without sharing my screen. So let me go ahead and share my screen, and let me make sure I am in fact sharing my screen. Okay, so our chapter 14 lecture is addressing correlation and regression. The majority of the chapter is focused on correlation, and I'm trying to see if I can launch it, and it's not letting me launch it. There we go. And so you cannot do regression without correlation. Correlation is kind of the foundation for regression, or the first steps for regression. But correlation is very different than the other types of designs we've done. Remember, back in the very beginning, we discussed kind of two different structures for research. One is correlation, where you're looking at two measured variables, and you're looking at the co-relationship between those variables. You're not really doing anything with the participants. All participants are contributing the same data, just one big giant survey where you're collecting all the same information from all the same people. You're not making necessarily comparisons between people in a correlational structure. You're really just looking at the relationship between the variables themselves. So we don't group anybody, we don't separate anybody, we don't differentiate between people within our sample and compare something between those groups at all. We merely look at their scores on one variable and compare their scores on another variable. So we're comparing variables to one another rather than people to one another. And that's different than the other studies that you've done so far. So when you're looking at a correlational data structure, you're dealing with two measured variables. There's no grouping variable, no independent variable, no quasi-independent variable. You're merely looking at two measured variables. And those variables, you collected data on, you observed them just as they naturally, fundamentally exist in the world. There was no manipulation, there was no pre-test, post-test. It's just right now at this point in time on a scale of 0 to 10, what's your happiness level? Right now, how much do you exercise a day? And we can compare exercise and happiness levels. Notice I'm not looking at comparing people who exercised more to people who exercised less. I'm not doing that. I'm only looking at amount of exercise every day and happiness levels, and I'm comparing the variables to one another. So we don't do any kind of control or manipulation or, again, comparisons between groups. So essentially you need two scores, at least two scores. We often, when we do correlational research, we are comparing multiple things, but you need at least two scores. And so we typically refer to one score as X and one score as Y. And we're looking at the relationship between X and Y. So for every single participant in your study, you have a value for X and a value for Y. So you always have at least two scores. And what we can do then, because there's two scores for a single individual, is we can create a scatter plot. So over here to the right is what you see is a scatter plot. So I'm going to focus on this bottom left-hand one. And if you take this bottom left-hand dot, that represents this person's score, where they landed on X and where they landed on Y. So if you look at this as an X and Y axis, right, where your horizontal line is the X axis and your vertical line is the Y axis. And the values go from 0 to increasing. And over here, the values from left to right go from 0 to increasing. So we can see that this score has a low X and a low Y, versus this score has a higher X and a higher Y. And what we want to see is there any kind of pattern that's emerging? Typically, when you see just a blob of scores and it just looks like a big giant circle, then we can typically conclude that there's no correlation there between those two variables. However, when you start to see a leaning or a tilting of the blob, and they start to have more of an oval shape to them, then there's usually a correlation. So notice this one is actually showing that it's kind of leaning to the left a little bit. It's more than a circle, they're kind of coming together a little bit, more like a bee, a swarm of bees, right? And this, it would be like, because they're not clustered really close together, they're not that connected. So it's a weak correlation. Over here, again, they're kind of now leaning to the right, but they're still, it's more of an oval shape, and that is going to be a weak correlation as well. When they start to get closer together, the correlation becomes a little bit stronger. So notice these are dispersed apart more. It's a weak correlation. And these are closer together, so it's a moderate correlation. Now look at the ones up top. See how really close they are? They're flying more in formation, right? And these are stronger correlations. So you can look at a scatter plot and determine, number one, is it likely that a correlation exists? We obviously have to do the math, but we can look visually and see, does a correlation exist? And we can see no, yeah, weak, a little bit stronger, and then here these guys look really strong, right? We can also tell the type of correlation. Is it a positive or a negative correlation? When it's a positive correlation, as one increases, if there's a high X value, there's also a high high Y value. If there's a low X value, there's also a low Y value. So they're either both low, both high, both medium, but they're traveling in the same direction. So as one goes up, the other goes up. As one goes down, the other goes down. That's what we call a positive correlation. You can visually see a positive correlation because they lean to the right, okay? Look at, as X is getting higher, the Y values are getting higher too. So for the high Y values, there's also a high X value. Versus over here, that's not always the case. Here's a high Y value, but it does have, it's not a high, it's a medium Y value with a high X value, right? Here you have a high, a medium, but a very low X value. So they're not kind of taking any particular pattern or shape, whereas these are. And when they're leaning to the right, it's a positive correlation. When they're leaning to the left, it's a negative correlation. Notice on this one, you have a high X with a low Y. So in a positive, it's high, high, low, low. In a negative, they go in opposite directions. So you have a high X, you have a low Y, or if you have a high Y, you have a low X, okay? So that's kind of the difference between a positive and a negative, and then we can see whether there's no correlation, a weak or moderate or strong correlation. And we can do that by looking at a scatter plot where each person in the data set has a specific plot representing the intersection of their X and Y scores. So we talk about those things as being the direction of the correlation or the type of correlation. So when I describe it as a positive or negative correlation, I'm describing the type or direction of the correlation. I'm telling you whether they travel in the same direction, they're going in the same direction, or they're going in opposite directions. Positive correlations go in the same direction. So X and Y both increase or they both decrease. And a negative correlation, that they go in opposite directions. As X is increasing, Y is decreasing. As X is getting lower, Y is getting higher, okay? We also can look at a correlation as telling us the form of the correlation. Is it a linear correlation? Is it a linear relationship? Is it a curvilinear relationship? Is it no relationship at all? So there are other forms that exist. We're going to focus primarily on identifying linear relationships in this class, but advanced statistics classes will help you analyze statistically curvilinear relationships as well. And then finally, we can look at the strength or consistency of the relationship. When we do measure or mathematically calculate correlations, they can range, they produce what's called a correlation coefficient, okay? And that coefficient can range anywhere from -1 to 1. And remember, that's on a number line. And it's a continuous variable, it's a continuous coefficient. And so it can, there can be any value in between -1 and 1. There can be -0.85, -0.23, and 0.76. So it can break down in fractions anywhere from -1 to 1. And the ones represent perfect correlation. For every change in X, there's a corresponding change in Y, and they're all changing in the same direction. And 0 represents no correlation. So I want you to kind of think of this as the Z-score. Remember our Z-score? And I'm just going to go ahead and share my screen. Remember when we had our Z-score, we talked about, you know, this was 0, right? Our mean was 0. And then we had 1 standard deviation and 2 standard deviations. And the further it got to the edges, the stronger the scores, or the more likely that Z-score was significant. Remember? The same is true for a correlation. Imagine this is -1 and this is 1, okay? When you have any value in between here, okay, the closer the value is to 0, whether it's positive or negative, the weaker the correlation. So smaller numbers, the absolute value of the number, we signify correlation with R. And so the absolute value of the coefficient, the smaller it is, the weaker it is. The bigger the number, the stronger the correlation. So values that then go up closer to the 1 on either side, it doesn't matter if it's -1 or a +1. Just like with a Z-score distribution, the closer it is to those edges, the stronger the correlation, the more likely it is to be significant, okay? So keep that in mind. Now I'm going to go back to sharing my PowerPoint. Okay, and so when you have a 1, either a negative or a positive, it's considered a perfect correlation. And then we want stronger correlations are more likely to be significant, okay? So here's a particular example where for every single person, you have 2 measured variables. We've measured their family income. So this family makes $31,000. This family makes $174,000. We've also measured their average grade. Now, I want you to notice something. I'm going to plot for A, 31,000 and 72%. So here they are, 31,000 and 72%. This dot represents person A. Person B, 38,000, so it's going to be over here, and 86. So maybe this one right here, right? This is likely person B, okay? So every single dot represents a participant in the data set. Now, I can kind of see, is this creating an oval or is it creating a blob? It looks more like it's creating an oval. So it's likely a correlation. Is it a strong or weak or moderate correlation? I'd say it's probably moderate, maybe weak. And then it also leans to the right. So I know it's a positive correlation. I can see that as for X values that are low, Y values are low. X values getting higher, Y values getting higher, right? Here's a really high X and a really high Y. So that's the general pattern. Now, if I take this dot away, you know, maybe it's not as strong of a correlation. This is going to pull that oval and make it look more oblong than it might be. So I can kind of see it from the scatter plot, but also notice, look at this. As these are increasing, so are these. You see that? That general pattern likely tells me, maybe they're a relationship. It's not a one-to-one correspondence, so I know it's not a perfect correlation, but it does look like there's a general pattern here. So you can look at the data itself and you can look at the scatter plot. Now, when I'm looking at these other examples, I can literally draw a line through the correlation, right? Remember I said we're looking at linear relationships. So I can draw a line through the plots and I can see how close are they hovering around the line. They're hovering around the line very closely, it's a stronger correlation. If they're not hovering around the line that close, then it's a weaker correlation. This is looking at the amount of beer sold and the temperature. So notice as temperature's going up, beer sales are higher. That's a positive correlation. It's leaning to the right, one score is increasing, the other is increasing. So low scores stay together and high scores stay together. In the relationship between coffee and temperature, it's the opposite. As temperature goes up, coffee sales are decreasing. Clearly not iced coffee, but coffee sales, okay? And so with high values of of X, we have low values of Y. They're in opposite directions, so it's a negative correlation, okay? Here's an opportunity for you to kind of identify, is there a correlation or not? So go ahead and hit pause and see what type of correlation. Would you consider it a weak, a moderate, a strong, or no correlation at all? And then would you consider it positive or negative? Okay, so I'll let you practice through those. And then assuming you have stopped me and started me again, here we go. This is a positive correlation, or excuse me, this is a negative correlation that's leaning to the left, but it's super strong. This is actually a perfect correlation where it is an exact straight line. They are all lined up on that line. So notice as we have really high X's, we have really low Y's. As we have really high Y's, we have really low X's, okay? And so that's a negative correlation. Over here, we're likely not seeing a correlation. It's just a circle, it's just a blob. So there's likely no correlation. Down here at C, we are seeing they're hovering. They're not exactly on a line, but it's probably a strong correlation. And also, we're seeing that it's leaning to the right. So we have high X values and high Y values and low X values and low Y values. So it's a positive correlation. Over here, yeah, they do form a little bit of an oblong, but it's still a fat oblong. So it's quite likely a weak correlation, but they are leaning toward the left, which means it's likely a weak negative correlation. So let's talk about statistically, how do we analyze correlations? We've talked about visually, we've talked about what they are, we've talked about strength and type, and now let's look at the actual mathematical inferential techniques that we use to analyze correlations. Pearson product moment correlation is the most popular correlational method that you'll see in the research. So when you're pulling research studies that are correlational in nature, they almost are always using a Pearson product moment. And in a Pearson product moment correlation, we're analyzing a linear relationship between two variables. Those variables both need to be scale data. So they're either interval or ratio data. And we signify a Pearson product moment with the letter R. So our notation for correlation is lowercase r. When we're looking at a perfect linear relationship, which as we already talked about, is either a -1 because it's a negative correlation or a +1, then we're talking about X and Y, the covariability between them is perfect. Exactly the direction that X moves, Y moves as well. It's a perfect correlation. So every single change in X has a corresponding change in Y. X goes up, Y goes up. X goes down, Y goes down. So they follow each other along that scatter plot. When we're talking about conceptually, what are we mathematically examining? We're examining the covariability of X and Y together in our numerator divided by the variability of X and the variability of Y separately. So their combined covariability divided by their individual separate covariability. Oh, it's not moving forward. Okay, now it's, there we go. Okay, so when we're looking at the actual formulas for Pearson product moment, we're going to introduce you to what we call the sum of products. Remember that when we did variance and we calculated variance, we looked at the sum of squared deviations. Remember, we looked at how X deviates from the mean, and then we squared that, remember? And then we summed all of those things, and that gave us the sum of squared deviation, what we symbolized as SS, the sum of squared deviations. And then we ended up using that in our formula for variance, right? It's sum of squared deviation divided by n for a population, and sum of squared deviation divided by degrees of freedom for a sample. Well, now we're looking at sum of products. Now remember, we have two variables. So we need to look at the combined effect of both variables, and what we can do then is multiply them together. So similar to sum of squared deviations, we're taking the X value minus its mean, right? That's mean subset X means the mean for X, okay? And then the same thing with Y. We're looking at how much does a given Y score deviate from the mean of Y's? How much does a given X score deviate from the mean of X? And we're timesing those times one another. We're multiplying, which means that we're doing a product, right? The result of multiplication is a product. And then we're gonna do that for every single X and every single Y in the data set. So for each participant, we take participant 1, their X, how it deviates from the mean, and the Y, how it deviates from the mean, and multiplying those together. And we do it for participant 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and sum all those together, and that's our sum of products. So this formula I really love because it lets you see the true definition of sum of products, and you can relate it back to what you already understand in terms of calculating variance. But if you want just a really quick and easy computational formula where you can just plug data in, and then this formula down here is a much more efficient formula to use just for the mathematical computation. I like this one so you understand what we're doing and how it relates to what we've done. And then the computational formula mathematically just makes more sense sometimes, okay? Either way, they end up producing the same result. Only the computational formula is a little bit easier just to do the math, okay? Okay. It just doesn't want to move forward. So this is just comparing the sum of squared deviation formula, right? Where we took the sum of all the X and how it deviated from the mean and squared it. So now our sum of products, very similar, right? And then also looking at the computational formula, because remember we also had a computational formula for the sum of squared. We also have one for the sum of products, okay? Come on, move forward. Okay, so when we now have those scores, we plug them into the Pearson product moment formula, and that equals R we take the sum of products divided by the square root of the sum of squared deviations for X times the sum of squared deviations for Y. So our sum of products is in our numerator, still relying on sum of squared because that's how we get variance for X and variance for Y, okay? And then we take that ratio and that tells us whether there's a correlation. So ultimately what we're looking at is the covariability for X and Y together, and the variability of X and the variability of Y separately, okay? I'm gonna have to stop. I'm gonna share my screen again. I'm gonna stop putting it in the presentation view because it's moving a little slower. So if I do it this way, it'll be easier to navigate. I know it doesn't come out as large on the screen, but bear with me, okay? Okay, so if we apply that to an example, This is a data set where we have 1, 2, 3, 4, 5 participants. They each have an X score and they each have a Y score, okay? So for this participant 1, they got a 0 on X and a 2 on Y, so this is participant 1. This participant got a 10 on X and a 6 on Y, so 10X and then Y6, so this is them. And then this participant got a 4 on X, which is right here, and a 2 on Y, so this is participant 3. See, each one of these corresponds to a participant. Now, when I do my calculations, right, I have an X column, a Y column. This is gonna be, I want you to see down here are just the means. So if I take this 16 and 4 is 20 plus 10 is 30 divided by 5, my mean was 6 for X. And then if I have 8, 10, and then 10 is 20, divided by 5 is 4 for Y. So I have a mean of 6 for X and a mean of 4 for Y. This is looking at my X minus my mean of X. This is my, so this is going to be 0 minus 6 is a negative 6. 10 minus 6 is a 4. 4 minus 6 is a 2, a negative 2. 8 minus 6 is a 2, and 8 minus 6 is a 2. Okay, same thing for Y. 2 minus 4 is a negative 2. 6 minus 4 is a 2. 2 minus 4 is a negative 2. So that's where these numbers are coming from. Now, I'm just going to square my deviations, right? So it's X minus the mean of X squared. So it's just negative 6 times negative 6 equals 36. 4 times 4 equals 16. Negative 2 times negative 2 equals 4. So that's where these are coming from. And then down here, I'm just summing all of these. I'm adding all of these, right? And that equals 64. I do the same thing for my Y. Negative 2 times negative 2 is 4. 2 times 2 is 4. Negative 2 times 2 is 4. So on and so forth. Add them all up. And my sum of squared deviations for Y is 16. I can't just add these up because if I add these up, they'll equal 0. I have to square them in order to have any valuable data I can work with, okay? For the sum of products, I just take this times this. So negative 6 times negative 2 is 12. 4 times 2 is 8. And negative 2 times negative 2 is 4. So now I have all the components I need. I have my sum of products, my sum of squared for X, my sum of squared deviations for Y. I plug them into my formula, right? So 28 is my sum of products. My sum of squared X is 64. Sum of squared Y is 16, okay? So I do, first I'm gonna do mathematically, then I'm gonna times these, then I'm gonna do the square root. So 28 divided by 32 equals 0.875. So the correlation we see represented here, first of all, it's a positive number. It's a positive correlation. Remember these dots lean to the right, so that makes sense. Additionally, if you draw a line through them, they're pretty close to the line, so we would expect a stronger correlation, which means the absolute value of the R should be higher, closer to 1, and see this is 0.875. So this would be a strong positive correlation. Make sense? Perfect. Okay. Now, let's look at why do we use correlations? Correlations are great because if we see that two variables are strongly correlated with one another, we can actually make predictions. So for instance, I know absences are correlated with grades. The more absences you have, the lower your grades. It's actually a very strong negative correlation. You can't, particularly in stats or research methods, you cannot do well if you're just not showing up to class. And so if I know the value of one, I can often predict the value of the other. If I know that you are here on a regular basis, I can predict that you're going to have a higher grade. If you're always absent, then I can predict you're going to have a lower grade. And so we know that we can use that correlation for prediction. Additionally, when we talk about validity, we talk about accuracy, right? And so we can demonstrate accuracy through really strong correlations, whether it's pre and post scores, whether it's two variables together, we can predict accuracy, right? we know one particular test is a really good predictor and it's highly correlated with another test, then that test is likely a good predictor as well. And then reliability is consistency over time. So if I'm standing on a scale and it's telling me I weigh 200 pounds one day and 100 pounds the next, that's not a reliable scale, right? I want a consistent, reliable score. And so if we see one score correlating with the other score, that's reliable. We see multiple people doing observations and that their scores correlate with one another, then their observations are more reliable, okay? And then also finally, we can use it to verify theories. So in a particular theory, if I can say like level of depression means that you aren't going to communicate as much and bond as much, so it might be associated with poor attachment if you're a new mother. And so that's a theory, right, where I'm looking at this relationship between attachment, and I'm presuming when you're depressed, you're not as engaged, and so you're not going to bond with your baby. I can look at your scores for bonding and your scores for depression, and I can correlate those, and if there's a strong correlation, then my theory is accurate. So I can verify that theory. Okay. So when we interpret a correlation, we have to be very cautious. Although we might even have a perfect correlation, it still does not mean that X caused Y. So when you're interpreting a correlation, you can never say that correlation is causation. Correlation is not causation. I cannot emphasize that enough. X does not cause Y. Absences do not cause poor grades. They're related to poor grades. The reason we can't say that absences cause poor grades is because we don't know. Maybe there's some third variable out there. Maybe you are dealing with a death in the family and it's causing you to be absent a lot, helping the family take care of, settling the estate, funeral arrangements, helping your mom grieve, whatever it might be. And so you then are being influenced, both your attendance and your grades are being influenced by this outside factor, by this other variable. Additionally, we don't know which came first. For instance, like you might say that absences can influence poor grades, but poor grades might influence absences. Maybe the poor grade, maybe, hey, I was here all the time, I was participating, I thought I knew what I was doing, and then all of a sudden I bombed a test. Now I'm discouraged, and maybe that's why I'm not coming. So because we can't determine, we call that temporal precedence, which came first, and because we don't know if there's some third variable out there, basically we cannot say correlation that X caused Y. So correlation is not causation. Additionally, now you have to think about the range of scores. Remember in that one example, I said, hey, this guy over here is an outlier. He might make it look like there's a bigger correlation than there is. When you have a restricted range and you're not seeing all of the data, it can also make you think there is a correlation when there isn't, or there isn't a correlation when there is. So if you don't have the full representation of the data or the potential scores on that data, on that value or variable, then it can be problematic. And so again, a good sample size comes into play. We want to make sure our sample size is large enough where we don't have a restricted range. And then when you have one or two extremes, those can be outliers and they can make it look like there's a pattern when there isn't. So outliers affect your scores and they can have a dramatic effect on correlations. Keep that in mind. So when you're looking at a correlation, sometimes we look at that coefficient and we might want to say, oh, it's halfway between, if we have a 0.5, it's halfway between 0 and 1. So, that's like a 50% correlation. Yeah, we don't interpret correlations in that way, right? So we have to recognize we cannot convert them to just pure percentages like that. That's not what they mean, okay? We can look at correspondence, right? Proportions, but not percentages. So again, I cannot emphasize this enough. Correlation is not causation. It's merely showing that X and Y are related. It is not showing X caused Y. Remember, the only way that we can establish causation and say X caused a change in Y is through a true experiment. True experiments involve control and manipulation. We have to be able to randomly assign people to one group or the other. We cannot do that with correlation. We're just gathering two measured variables. So in a true experiment, there's a manipulated variable and a measured variable. We do not have that in correlation. We only have two measured variables. And so consequently, we can never say that there's a causal relationship between those two variables. So here's an example. There is a really strong correlation between number of churches in a city and the crime rates. So does that mean churches are causing higher crime? That doesn't make sense, right? There's actually a third variable out there that's probably causing that relationship. And what it is population. Big cities have more churches because they have more people to accommodate, and they have higher crime rates. So that third variable is causing the relationship, or I should say that third variable is likely explaining the relationship, not churches causing the crime rates. Okay, here we are. And so when we're talking about restricted range, here's an example. We only have these values right here. It would look like there's no correlation. But if we saw all of the potential scores, if we had participants that represented data across the full range of X and the full range of Y, then now we can see, look at, there's a correlation. So we have to look at correlation and restricted range. Be careful, like when you know you're studying a variable like IQ and you know what the range of IQs are, but you only have a bunch of people that are just genius level IQ, that's problematic, right? You need the full range in order to draw any really accurate conclusions, okay? It's not moving as well as I would like. And here's an example of how outliers can be problematic when we're looking at this correlation. This is just a blob. It actually results in a negative correlation of 0.08, which is not significant. So we would say there's no correlation between these variables. But then when you add an outlier in, all of a sudden, now look at it makes it look like there's a correlation. Here we have an oval. It's a skinnier oval, so it's likely stronger. When you run it through the math, it's a correlation of 0.86. Really and truly, maybe this guy's just uniquely different than the rest of the group, and these variables aren't in fact related. So outliers, particularly extreme outliers, can really inflate your correlations and make it look stronger than what it is. So pay attention to your data. In terms of the strength of the relationship, we just like how, remember when we did an F-score, we couldn't necessarily, all we could see is that, look, it told us there were significant differences, but we didn't know the magnitude of the effect, right? And that's what we used our effect sizes for, to tell us the magnitude of the effect. In correlation, we do the same thing. So where we truly want to look at the magnitude, we look at a coefficient of determination, and that's R squared. Now that should sound familiar to you because that's one of our effect sizes. And it tells us the percentage of variance accounted for in X by Y. And it's essentially measuring that proportion of variability. And so when you have an R of 0.80, so a 0.80 correlation, and you take the R squared, 64% of the variability of Y is predicted or accounted for by X. So R squared is officially called the coefficient of determination, and that effectively is our effect size for correlation, okay? Okay, and then when we're doing hypothesis testing with correlations, we remember any particular research question can be submitted to a hypothesis test. You have to identify what technique is appropriate. When you're looking at the co-relationship, you're not dividing any groups or making comparisons between any groups. You're just looking at two measured variables and the relationship between those variables. And both of the variables are scale data, interval or ratio. That's going to be a Pearson product moment. When we write out our hypotheses, we typically write out our hypotheses in parameters, and how we notate the correlation in for parameters or for populations is through this row. See this fancy little P? We call that row, okay? So for our null hypothesis, we're saying that the correlation is going to be 0. For our alternate, we're saying it's not going to be 0. It's going to be there. So the null translates as no population correlation. The alternate translates as there is in fact a correlation. In a directional hypothesis, I always start with the alternate hypothesis, and I say, what direction am I expecting it to go? In this case, rho is going to be greater than 0, so I'm predicting a positive correlation, and then your null is going to be everything else. So you just flip the greater than to a less than and add an equal sign. For this one down here, I'm predicting that the correlation is going to be less than 0, so I'm predicting a negative correlation, and so my null is just going to be flip that less than sign to greater than and add the equal to, okay? Okay, so when we're doing a hypothesis test, and a null hypothesis says no correlations expected, and so we would expect the sample is going to have any difference between, if there is even a small correlation, it's just due to sampling error. It's not because there is actually a correlation between the variables. In an alternate hypothesis, we're looking at, no, that value does absolutely represent a correlation and more than sampling error. Okay. Now we are still, once we calculate the correlation, we actually apply a t-test or an f-test to determine if that correlation value falls in the critical region. And if it falls in the critical region, then it's said to be significant. So we will apply a t-test, right? So the sample statistic minus the sample statistic minus the population parameter divided by standard error. And how that is going to be signified is when we're looking at the final t statistic, we have our sample correlation minus our population correlation divided by standard error. New formula for standard error, just like with every other formula, standard error is adjusted. And so, because remember, we're estimating standard error from sample data. So the formula for standard error in a correlation is 1 minus r squared. So you need to calculate that, that coefficient of determination, and divided by degrees of freedom. And minus 2, when you have x and y, it's 2. A fixed data point for x and a fixed data point for y. And the square root of that is your standard error. So what I do is I first calculate my r, then I calculate my r squared, and then I can plug that into my overall formula. Remember, we're always testing the null hypothesis, so it'd be our r minus 0, okay? The first thing. Okay, in the literature, when you actually look at published research, how you see this written out is we see a correlation for the data revealed a significant relationship between the amount of education and annual income. Our correlation value, our sample size, our p-value. This was not necessarily done in SPSS. If we've done it in SPSS, we would put the exact p-value, and then whether it was a two-tailed or a one-tailed test. So notice I need to be able to identify my variables here are education and income. Here's my correlation coefficient, my sample size, my p-value. Also, if I have more than 2 variables, you will see a correlation matrix. And often in research, we don't study just the relationship between 2 variables. We're looking at gathering data on multiple data points. So there might be an X, Y, Z, W, L, M, N. There might be all kinds of variables in that study. And a matrix would show the correlation, every possible combination of correlation between all of those variables. And typically we would it's a matrix of all the coefficients, and then we would put asterisks if it's significant, and we'd put a footnote. One asterisk also often means significant at 0.05. Two asterisk means it's significant at 0.01. So that's quite often what you see in the literature. Okay, so now's a good time to take a break. I would take a break, stretch, get a snack, walk around a little bit. But I am going to go into different types of correlation. We do, although Pearson product moment is the most popular correlation, you will in fact see multiple correlations. This chapter has you calculating different types of correlation. The trickiest part is figuring out which one you use. So Pearson product moment is when we're comparing two variables that are both scale data, okay? When in a Spearman correlation, we signify that as R subset S, see that? You have two ordinal variables, so they're ranked variables. I might know where you're ranked for second, third, fourth in your class, and where you're ranked in absences, okay? So that's an alternative to Pearson, still looking at the X and Y, but now we're looking at a ranked data, okay? So the example is I look at how much did you practice and where do you rank in performance? And I can look at that relationship. A point by serial correlation is when you actually have one numerical variable, so you have one scale data, and then you have one binomial or dichotomous, nominal, where there's only two choices. It's black or white, okay? So a point by serial, you're correlating black or white compared to a scale variable. What is the relationship between those two variables? And finally, there's the phi coefficient, signified here by a phi. And that's when you're looking at two dichotomous variables. So you're comparing black and white and high or low, right? And so you have to look at what is the data structure. What's the research question? If they're looking at the relationship between two variables, not comparing groups, then it's a correlation, right? If they're two measured variables, then you look at the type of data. If you have two scale variables, it's a Pearson. If you have two dichotomous variables, it's a phi coefficient. If you have two ranked variables, it's a Spearman. If you have one dichotomous and one scale, it's a point by serial. Now, when you get into the nitty-gritty of these can be a little bit confusing because they do resemble other techniques, and we'll talk about that in a second. So here's a Spearman row where I'm looking at the relationship between amount of practice and level of performance. And you might see, look, as you practice more, you get really good, but then it kind of levels off, right? This might be revealing more of a curvilinear relationship. It's making me so mad that I can't just move forward. When you do a Spearman correlation, what you actually have to do is you actually take all their ranks. So you graph it and it's just in its original form, and you convert the ranks or the mean of ranks. And then what you end up doing is applying a Pearson technique. So you convert the ranks to scores. So you rank them, you convert the scores to they're already ranked. You end up plotting them out in their original set, and then you say, okay, B in terms of X, B was first, second, third, and fourth. And then in terms of Y, B was first, second, third, and fourth, right, in terms of values of Y. And so then I rank those and I run those as a Pearson product moment now. So when you do a Spearman correlation, both of your data are normally ordinal first, they're ranked. So I am going to apply the Pearson correlation to the ranks. So I'm actually going to input the ranks rather than the original scores per se. If it's interval or ratio, or if there are two variables that are scale, I can use a Pearson product moment. Okay, this actually, when I can actually be analyzing a monotonic relationship, which when I have two variables, is there a consistent direction of the relationship? Okay, mono kind of, yeah, maybe that's not a good, I'm gonna hold back on that. So we pretty much can just rank them smallest to highest and then assign their rank, right? And when there's scores that might be tied, like you have two with the same exact score, I can take the mean of those and use that for their ranking, okay? So assign the mean value for the ranks. And then here's a new formula that I'm going to use. I have a new sum of squared formula. I have a new mean formula. And then I have a new RS formula that I can use to calculate a Spearman. Or I can just put the ranks into SPSS and it'll calculate for me. Then in a point by serial, I have two dichotomous variables. So I'm going to code those as 0 and 1. And then I'm going to, again, apply the Pearson product moment formula. When I'm looking at when I'm looking at a point by serial, because I have one dichotomous variable and one scale variable, it can be confusing because it's similar to an independent measures T, okay? But you wanna look at, am I intentionally looking at a relationship between just two variables, two measured variables, or am I specifically looking at breaking people into groups and doing a comparison between groups? You want to understand the difference. Looking at a T-score, it's telling you it's looking at mean differences between the two groups. And the R-score is looking at the correlation between the two variables. Very different kind of questions that you're being asked, okay? But we're going to code the dichotomous as 0 and 1, and then we're going to plug in the actual data for the other variable. And then we're going to run a correlational analysis, again, using the Pearson product moment, and it's going to end up giving me an R value, okay? And then finally, the phi coefficient, where you have two dichotomous variables. And this can actually kind of resemble chi-square, which you haven't studied yet, but be careful, chi-square uses frequency data. This isn't necessarily using frequency data. And so again, it's asking a different question, okay? And then again, we use R squared for the effect size. Most commonly in statistics, you're going to actually see a Pearson product moment. It's rare to see the other ones used, okay? Okay, so for us, and I don't want you to necessarily have to run them, but I do want you to differentiate when you use one from the other. And then in SPSS, we're gonna do our data entry. I'll post an SPSS instructions for correlation in your module, so you'll be able to see that on Canvas as well, okay? So it's fairly simple, okay? So now is a good time to take a break. You wanna go ahead and shut the pause button. We're gonna move into linear regression. It's not gonna be a detailed discussion of linear regression because this is an introductory statistics class, so it's just giving you kind of the basics right now. But a correlation, linear regression is very commonly used in statistics. And so as you advance in your education and you take higher level stats classes, you're gonna see regression used more often, okay? So let's go ahead and dive in a little bit. When we talk about regression, remember back when you were in high school and you did like linear algebra or maybe some trig, pre-calc. Not all of us went that far. I hated it. But that being said, if you had the opportunity, I remember actually there was equations that corresponded to lines. And I'm like, why do I have to calculate this equation for this line? It didn't make sense to me. I was like, what the hell? What do lines and equations have to do with one another? Regression. That's exactly what they have to do with one another. There's an equation that corresponds to every single line. And when we see an equation, we can map out a line, and when we see a line, we can calculate the equation. It's pretty fascinating. But that now line allows us to kind of see where the line is centering on the data, the relationship of the data to the line, and the line kind of represents that midpoint, that mean that drives through the data points. And it allows us a baseline and a way to kind of make predictions and estimations based on that line. So the line is an important tool, and the equation that corresponds to that line allows us then to make precise predictions. So if we know a value of X, we can predict a value of Y based on the line that we know runs through those correlation points. So the regression line first allows you to determine which straight line is the best fitting line for that particular data set. And the best fitting line is the one that has minimal prediction errors. So we'll talk about this here in our next slide, where I can draw a line through these data points, right? And looking at them, they're likely a strong correlation. I draw a line through, and then I can measure the distance from each data point to the line. So there's a distance here from each data point to the line. Distance from each data point to the line. The line with the least average distances is our best fitting line. It's the line that represents the greatest predictable quality or precision of predictions, okay? When we talk about linear equations, we have a linear equation. The general formula is we have our y equals slope represented by b times the x value plus the y-intercept. So here I'm giving you definitions of the notation. X and y actually correspond to precise data points on that scatter plot for one single participant. Slope represents the change in y based on the x value, and the y-intercept is actually what the value of y is when x is 0. So at what point does it intersect the x-axis? And then we're looking at, I personally don't love this example, but I know it's in the older edition of the books, or the older editions of the book. But it's letting you see, okay, local video store has an annual membership of $5. So you don't even have to rent 0 videos and you're gonna pay $5, okay? And then you can rent, if you have a membership, you can rent videos for as little as $2 each, okay? And so with this, we can kind of figure out where those numbers fit. And so we're saying, okay, I am looking at the slope as $2, right? So if I'm looking at X as being the number of videos that I rent and Y as being my total membership cost or my total video cost over time, then I'm gonna say $2 is my slope, right? It's increasing by X. And then $5 is my intercept. So assuming I rent 0 videos, then I'm still paying $5. So I can now use this formula, y equals 2x plus 5, to calculate what my total cost of membership is if I know how many videos I rent. So if I rent 10 videos, 2 times 10 is 20, plus 5 is 25. I'll know then that my total membership costs were 25, okay? So I can use that line to predict y or to calculate y based on a known value of x, okay? So it's a prediction tool, a precise prediction tool, and that's very valuable as researchers because prediction is our first step to solving problems, right? If I can predict that absences are, if I can predict your grade based on absences, I can intervene when you have a certain number of absences, and I can do my best to try to make sure that I'm supporting you and supporting your success instead of letting you fail, okay? Okay, so when we're looking at, I'm not gonna go through this, we don't need this. Okay, so here's a learning check. You can just hit pause and go through these yourself. You're never gonna have to do like a full-blown regression analysis, but you do have to do predictions and calculate what y is based on x. And so this is allowing you to do that. So go ahead and hit pause and work those through. And assuming you hit play again, we're going to look at a gym charges $25 a month. That is your membership fee, plus you have to pay $2 per hour for aerobic classes, which sucks, right? So $25 monthly fee, plus $2 per hour, so X is the number of hours you go to class, and then Y is your total overall cost, okay? And then if I have this particular linear equation, what happens to Y each time X is increased by 1 point? So essentially it's letting me know that if this increases by 1, right, for every increase in X, Y is gonna increase by 3 points, because if I'm gonna go ahead, or it's gonna decrease, not increase, because that's a -3. If I go ahead and times -3 times 1, then it's saying Y is gonna increase by 3 points, okay? So using this linear equation, determine the value of Y for X value. I would just plug in 1 for here, 1. So 2 minus 7, my X is gonna be -5, right? If I take 3 times 2 is 6, minus 7, my Y is gonna be -1. And then 5 times 2 is 10, minus 7, my Y is gonna be 3. And if I take 10, 2 times 10 is 20, minus 7, my Y is gonna be 13. That's simple, okay? Okay, so these are helpful because again, I can use them for prediction. So when I am looking at something as simple as like how much TV do I watch? If the average person watches 5 hours of TV, then the closer you are to the mean, right? If you watch 5.5 hours, then your prediction's more accurate, right? So it's gonna be more similar to the mean, and there's not as much variability. So when you have, remember, variability is like static, so the more variability you have, the less precise your predictions, the less clarity you have when you're trying to analyze things. The same is true when you know two variables are correlated. The stronger the correlation, the more you're able to make accurate predictions. So if you know if there's a correlation between how many hours I work and how much television I watch, if you know how many hours I work, you can probably predict how much TV I watch. If I work like 100 hours a week, I'm probably not watching as much TV as someone that works 10 hours a week, right? So just like a mean kind of is an anchoring point for you, in regression, the best fitting line is that anchoring point for you. So linear algebra comes into play. That linear equation is that anchoring point for us. Stronger correlations allow us to make more precise predictions and find a best fitting line that has the lowest, that minimizes our probability of making errors in those predictions. So overall, when we talk about regression, it's a statistical technique that we use to determine what is the best fitting line, which of the lines, because we can draw multiple lines through a set of points. What line is the best fitting line? And that best fitting line is what we call the regression line. So the linear regression equation for the best fitting line is we have y hat, right, which is the predicted value. We call that a criterion, right? Y hat equals slope times x plus the y-intercept. So now we're using it for prediction, not just calculation, but actual prediction, okay? And so couple examples when we're looking at a linear equation, we want the best fitting line between high school GPA and college GPA. And based on our data set, here's our regression line, right? So we were able to, so if we have Sue's high school GPA of 3.85, then we want to know what her predicted college GPA is. We're going to first plug everything into the formula where we know the value of x, right? And we know the slope, 0.65. And we're going to calculate out her, if she has a 3.85 in high school, she will likely have a 3.552 in college. Actually, research has shown that GPA in high school is a stronger predictor of your GPA in college. Thankfully, that wasn't the case for me because I was a high school dropout and I graduated with honors from college. So, okay, let's see. Okay, so I did add a couple of videos so you can, if the book isn't clicking and this lecture isn't clicking, feel free to watch the video where it's helping you understand more about regression lines and where we get the regression equation from. And additionally, you know, it helps to hear it multiple ways. I will have another video too, I think. Okay, and so our regression equations, we actually now have two choices, okay, where we have the slope of B or B1, and we can mathematically calculate these. You'll never have to. You can use SPSS to do your regression calculations, and I won't necessarily have you actually do regression calculations, but I will have you use the regression line to make predictions of X based on a known value of Y. But you are going to see that the line's going to go through your mean of X and your mean of Y. So you can actually calculate that y-intercept or that slope of 0, okay? And here's the way that we can calculate the y-intercept. So sometimes you might have to calculate the y-intercept. Sometimes you might have to calculate slope. And then what you can do is you can plug all this into the formula to actually run a regression analysis. So when we're talking about a regression, y hat is our predicted value of y. And then y minus y hat is looking at the distance from each single data point to that predicted value. That's what we call the error of prediction. This is how we're able to kind of determine which is the best fitting line, right? And the regression procedure that we use, what it does is we actually square those distances, and it's going to find the line that represents the smallest squared error of prediction. So we call that the least squared error solution. So regression analyses allow us to find that best fitting line based on the least squared error solution, okay? And just a couple of things about correlation. Again, about regression. Again, when you have that negative slope, it's corresponding to a negative correlation. So the sign of the correlation will tell you the kind of slope you have. It's a negative correlation, it's going to be a negative slope. A positive correlation is going to be a positive slope. You don't have any correlation, then it's going to be a horizontal line. There's no slope, and actually we wouldn't do a regression analysis. We only do regression analyses when there's an established correlation between those two variables, okay? And the point at which the mean of X and the mean of Y intersect will always be somewhere on the line. So you might have other lines that are over here or over here, but the regression line is always going to have that intersecting point, that midpoint where the mean of y and the mean of x intersect is going to be on that line. So that's a tool for us to determine whether it's a best fitting line. If we don't see that intersection on the line, it's not the best fitting line, okay? When you have a positive correlation, all of your points that are above x will also be above the mean for y. And when you have a negative correlation, if it were flipped the other way, it's the opposite, okay? Where y is below the line, x will be above the line, okay? Okay, so here is our formula for the least squares solution, or R squared. Notice that capital R, this is our symbol for regression, essentially least squares solution. Here is our formula, right? So we have to break down and individually do all of the x from the mean. How does it deviate? What's the sum of all the x from the mean deviation? Same thing for y, right? How does it deviate? And then we have to draw that regression line and figure out the estimated, use that to figure out our estimated values of y, or predicted values of y. We're going to take the distance from the estimated values of the mean. This is how we symbolize that. And then we square them. And that is going to give us the sum of the squares. And plug that into our formula, and that's how we're going to get our least squares regression. Again, I will never have you do this manually, and what you will have to know how to do manually is calculate slope, calculate a y-intercept, and make a prediction of y. If you're given a formula, make a prediction of y based on the known equation, okay? Again, we're looking at the distance of each score to y, and as we're squaring those, our whole goal is to find that equation that has the minimal distances, okay? Okay, so here is an extra resource and video on a standard error of the estimate. So walk through that as well, and it'll give you some additional information on calculating it. Again, you'll never have to do it manually in this class, but you may in future classes, so it doesn't hurt to better understand it. We are looking at R going from 0 to 1. So plugging our formulas in. Again, this is to calculate standard error of the estimate. So remember, we change our standard error formula for every technique that we use. And so this is introducing you to how to calculate the standard error that corresponds to regression, and we reference that as standard error of the estimate. And what we know that as R gets bigger, your standard error decreases, okay? And so here, in fact, is looking at the sum of squared for the regression, right? Here's our formula. Sum of squared for the residual, here's our formula. So basically our standard error of the estimate, here's our formula, okay? Again, never have to do it manually in this class. So we can use SPSS to determine the y-intercept and the slope of the line. This is going to take you through the techniques to do that and the symbols. We do want to be really careful, because know that predictions aren't perfect. There's always a probability of error, so there's always going to be some differences between our predicted value and the actual data itself. We are, of course, trying to minimize that, and that error might be different for each point on the data set, right? Because if it's further away from that regression line, it might have a larger error than another data point that's closer. So what we do is when you have stronger correlations that are closer to 1 or -1, then the data points are usually clustered, so it'll have minimal error, but weaker correlations are going to actually produce more error, okay? We don't want to make predictions for X values that are not within the range that's covered in our data set. We have to be careful about that. Remember, if we have a restricted range, it's problematic in general. So we can't make predictions if we've never, if the value or that range has never been in our data set, okay? And then also, when we have a curvilinear relationship, we can't use regression analysis. This is only for linear relationships. Just like with a correlation, we test whether it's significant. We are going to go through a hypothesis test. So we have a null hypothesis and alternate hypothesis, right? When we talk about slope, we talk about B or beta as being 0 in a regression, a null regression analyses. And then we're going to submit it to an F test to determine if it falls into the critical regions and whether it's significant. So here's actually the F formula that you would use if you wanted to calculate it manually. Just like with ANOVA, trying to calculate it manually is lengthy, time-consuming, confusing, but doable. Okay, so essentially when we're talking about a regression analysis, we're partitioning the sum of squared deviations, the degrees of freedom. And so we're taking our sum of squares for the regression. How much of that variability is due to the regression, the predictable line, versus just our error, right? Just our measurement error. And then same with degrees of freedom, okay? And so ultimately, what we're doing with a correlation, when we're seeing if it's significant, we do the same thing with a regression analysis. If the correlation's not significant, we really don't do a regression analysis. We do regression analyses for significant correlations. And we're just trying to find the best fitting line that we can use to make accurate predictions. And that's it for correlation. So you let me know if there's any questions. I would focus primarily on correlation, not as much on regression. You're gonna have limited exposure to regression, and you'll build on these basic foundational skills as you advance in your academic career. So hope that was helpful, and we'll look forward to talking to you in class.